All right. Hello, grade 12s. We are back with another physics lesson for you today. I've got a few important notes that I want to discuss just before we get started on today's lesson. So if you are struggling with some questions or anything inside of the work, I've had few students email me asking if they can ask me questions over email. And yes, of course, that's totally fine. That's going to be one of our main forms of contact. You can definitely also send me questions here on the Google Classroom where I post the videos, or more specifically on the YouTube channel where the video are posted as well. So you have three spaces there where you can send me questions or comments, but those will have to be answered electronically via text. Now in physics, that's not always the best way to do things. So what I'm going to do is on Tuesdays and Thursdays during our regular class time, so that is right around 11:30, for anywhere between 30 minutes to an hour, so it could be our full class time depending on how many of you there are present. I will be available the entire time. You can drop into the Google Meet that I'll post the link for on the classroom. You can drop in live and we'll have a video conference or a video chat live where you can ask me questions and I can work through the solutions to those questions with you. So that's going to be an option for you on Tuesdays and Thursdays during our regular class time. So if you want to come in, you can even just pop in to say hello. We can keep that contact up, and also I can help you out with any problems you might be having. It's a little bit easier for me to work through questions with you if I can show you what I'm doing on a piece of paper while we are doing it. So if that interests you, just make sure that you're keeping an eye on the Google Classroom, and I'll let you know when we are going to have those sessions. Tuesdays and Thursdays during our regular class time, in case you wanted to just write that down right now. So that being said, I will be on here tomorrow doing that. But as for today, we'll just do a regular lesson. We're moving onwards with momentum and the conservation of momentum in one dimension. So we are going to do a problem of the day. And our problem of the day today, the theme for today, the day of the year, is it's International Puppy Day. So it's International Puppy Day, and that means that our question is going to be about puppies. So a soccer ball is rolling with a velocity of 0.4 meters per second east, and a puppy runs into that ball with as much force as possible, 200 newtons. If that soccer ball is 0.9 kilograms and the impact between the puppy and the ball lasts for 2.1 times 10 to the negative 2 seconds, what is the final velocity of the ball? So I'm going to give you an opportunity right now to pause the video. Okay, you can pause the video and work on this question. Try to get a solution. Keep in mind that this question we have a change in velocity, and therefore we're going to have a change in momentum. So we need to relate the force and the time, the impulse, to the momentum. So Ft equals mv, and you should be able to solve it like that. So pause right now if you need to and work on it. If you aren't pausing, or if you just want to work on it right now, you're not going to have a whole bunch of time because I'm not going to wait here for about 5 minutes until you have finished working on it. So just give it a pause and we will move on. So if you did the problem properly, you would get that impulse is equal to the change in momentum. So Ft is equal to m times v2 minus v1. So our force was 200 newtons. Our time was 2.1 times 10 to the negative 2 seconds. The mass of the soccer ball was 0.9 kilograms, and we are trying to find the final velocity. So the initial velocity that it was moving with was 0.4 meters per second east, and then a force hit it further in the eastern direction. So our final velocity is 5.1 meters per second east. I hope that we were able to get that, 5.1 meters per second east. If not, you can continue. There's lots of questions like this in our last set of slides, in our last set of notes, and the appropriate corresponding practice problems for that. So let's move on. we are going to do today's notes on conservation of momentum in one dimension. So conservation of momentum in 1D. So you can find this in your note booklet. The page should look like what you're about to see on your screens now. So we have the principle of conservation of momentum is going to be our focus today. Let's do a little derivation here, a little visual derivation of where the conservation of momentum formula comes from. To derive the conservation of momentum, we have to examine a collision between two imaginary masses, m1 and m2. So what I have here is that I've just decided that the positive direction is going to be to the right and the negative direction is going to be to the left. So before that collision, you have the two objects themselves. M1 is moving to the right with an initial velocity of v1, and M2 is moving to the left with an initial velocity of v2. So the key here that you'll notice is now, because I have two different objects, I'm calling them M1 and M2, so their velocity becomes v1i and v2i, where the I just stands for initial. Okay, so you've got an initial velocity. When those two objects are hitting each other, they feel a force acting in the opposite direction due to the other object. So M1 feels a force F2 from M2, and M2 feels a force F1 from M1. So this is an application of Newton's third law, where we have every action force has an equal and opposite reaction force. So after that collision, we now have both of these objects moving in their own direction with a final velocity. That's where we have the F, V1F, and V2F, and they are off in their own ways. So these two objects have bounced off of one another. So what we get if we set up this equality is that we have the negative direction of F2 is equal to the positive of F1. The forces, remember, are equal and opposite. That is Newton's third law. So forces are equal and opposite. Now what I can do is I can replace the forces with the formula for them, mass times acceleration. That's Newton's second law. So we get negative m1a1, where the ones just mean that it is the object number one, and m2a2 is object number two's mass and acceleration. And then what we end up doing is we replace a with one of the very first formulas we learned in this course, that it's delta v over delta t. So we have v1f over minus v1i over delta t, and then on the other side we have v2f minus v2i over delta t on that side. Now what we end up doing is we can notice then that our t's are going to cancel, right? I have a t on this side and a t on that side, and they're the same, just like when we were talking about those projectile problems in kinematics. Time doesn't change for either object, so those are the same and they will cancel. So what I'll end up having then is just m1 times v1 f and m1 times v1 I, and then I have m2 times v2f and m2 times v2 I. And what we end up getting is the formula below right here. Now, we can actually make this even more simple, because what we can do is we can, let's put all of our final velocities and momentums, and masses on one side, and let's put our initial velocities and masses on the other side. So what I have now is m1v1i, that's the initial velocity of object one, the initial momentum of object one, and m2v2i, that's the initial momentum of object two. And that is equal to, look, I'm adding up m1's and v1's, the finals, so the mass one's final momentum, and I can add up mass number two's final momentum as well. And what we end up getting is that the momentum initially of the first object added up with the momentum initially of the second object is equal to the momentum of the first object after. and the momentum of the second object after. That's where that P comes from. Remember, P means momentum. So what does all of this mean? What is all of this telling us? What it's telling us is that there is a conservation of momentum. This is probably not the first time you've heard about the idea of conserving things. Maybe you've heard of the conservation of mass in chemistry, right? When you're balancing equations. This is no different. What it means is that the total momentum of all the objects before the collision is going to be equal to the total momentum of all the objects after the collision. So what we end up getting is total momentum before is equal to total momentum after. So total PI is equal to total PF. So that is our equation for today, our new equation that we're going to use. So we can move on. And you should see that formula on your formula sheet or something similar to that. Now let's move on to talking about the different types of collisions. There's 3 types of collisions that we're going to see in this course. Okay, the first of which being an elastic collision. So no matter what collision we're looking at, assume that there is no loss of momentum due to friction or air resistance. Okay, so there's no loss of momentum. So momentum is conserved. We're following that conservation of momentum principle. Now, what is an elastic collision? An elastic collision is when 2 objects collide and rebound. So the mass of each object does not change after each collision, and the objects remain separate before and after. So we'll do some examples here. Let's take a look at a before and an after. So before the collision, these 2 objects, like we kind of saw on our last page, are just approaching one another like this. Okay, there they are before the collision. Now, what happens is after they rebound, nothing changes. Their size and their mass doesn't change. So I'm going to try to draw these to be similar sizes. And we get A is moving just in the opposite direction, and I wrote just B was a little bit bigger, and B is moving off in its own direction as well. So what we have here, the key is that the 2 objects collide and rebound. The mass of the object stays the same, and that they just move in their opposite directions afterwards. So that's the only thing that changes is their direction. Now, in inelastic collision, this is a little bit more of a realistic scenario. This is something that we'll see more often in real life, is that 2 objects collide, but then they are locked together, or they kind of attach to one another during the collision. Okay, so before the collision, there's 2 objects, and then after the collision, they act as one single object. So again, let's take a look at this visually. Before and after. Let's use just some cars and or big and small cars as an example. I'm not going to try to draw them. They're just going to look kind of like carts. So here's one. We've got a larger object here. Okay, and then we have a small one, and actually doesn't even necessarily need to be moving this small one. Could just have an initial velocity of 0. And then, so this could maybe look like something like a rear end of 2 cars, okay? So a car is rear-ending another car. So the bigger car is going to go and collide with the smaller car that's not moving, but what ends up happening is the 2 objects after are stuck together. So we've got a little bit of damage maybe done to both of them, but they are stuck together and they're both moving in one direction after. That is an inelastic collision. Finally, our third type is an explosion collision. So it's not necessarily a collision, it's almost the opposite of a collision. It's the opposite of inelastic. Initially, there's only one single object, and then through whatever process, it either breaks into 2 or more pieces that move in different directions. So before and after. Well, before, let's use just maybe the most simple example. Before, we've got a little, some sort of explosive. okay, all in one piece. And then after that explosion, let's say this one breaks into, say, 3 pieces. Something like this. And they're moving in a whole bunch of different directions. So this is probably the most complicated problem that we can have because we're going to have multiple different directions that we have to deal with. Okay, so first off, elastic, no sticking together at all. Second, inelastic, objects start off as 2 and end up as 1. And then third, explosions, objects start off as 1 and end up as 2 or more. So we are just about there. We're going to do 2 examples together, and then I'll get you to work on the practice problems on your own if you haven't already gotten there yet. So a basketball with a mass of 0.7 kilograms and a velocity of 2 meters per second, and a soccer ball with a mass of 0.4 kilograms and a velocity of 0.2 meters per second are rolling towards each other on a gym floor. The 2 objects collide and rebound in the directions that they came from. If the basketball rebounds with a velocity of 1.5 meters per second, what is the velocity of the soccer ball after the collision? So our main formula that we're going to use for problems like this is that the initial velocity, the initial momentum and mass is going to be equal to and opposite the final momentum. I'm going to use I's and F's now. I'm going to use a subscript of B for the basketball, and I'm going to use a subscript of S for the soccer ball. Okay? So a subscript of B for the basketball and a subscript of S for the soccer ball. Okay, so what I need to do is I need to decide on a positive and a negative direction. Even though this one didn't necessarily give us positive or negative directions, I still want to know if my answer is going to be a positive or negative number. So let's set it up like that. And then what I need to do is break this down into its 2 separate momentums of the basketball and the soccer ball. So PBI, that's the momentum of the basketball initially, plus the momentum of the soccer ball initially, is going to be equal to, it's all conserved, the momentum of the basketball final and the momentum of the soccer ball final. So there we go. PBI plus PSI is equal to PBF plus PSF. And then the last thing that we need to do here is we need to replace the momentums P with MV. This is the key. So each of these are going to get plugged in right there. So then what we'll end up with is M of the basketball times the velocity of the basketball initially plus the mass of the soccer ball times the velocity of the soccer ball initially equals the mass of the basketball times the velocity of the basketball final plus mass of the soccer ball times velocity of the soccer ball final. There we go. Ends up turning into quite a long formula. But now we can take a look at, we actually know everything that we need to know to be able to solve this. We know that the mass of the basketball is equal to 0.7. The mass of the soccer ball is equal to 0.45 kilograms. Okay. The initial velocity of the basketball was 2 meters per second. So VBI is 2 meters per second. The initial velocity of the soccer ball is 0.2 VSI, but it's in the negative direction. We'll say the soccer ball is going this way and the basketball is going this way. So we'll say negative 0.2 meters per second. They do have to be going in opposite directions because they're meeting each other, right? And then the only other piece of information we know is we know that the final velocity of the basketball, VBF, is 1.5 meters per second. But it was initially moving in the positive direction, and then it bounced off of the soccer ball. So it's going to be returning in the negative direction, right? If the soccer ball and the basketball are approaching each other like this, basketball, soccer ball, sorry, they should be opposite. I've got the soccer ball in the wrong place. So this should be the soccer ball right here. So if the soccer ball and the basketball are approaching each other like this, they're going to rebound the other way afterwards, right? So that's why the final velocity of the basketball is going to be negative. And what that should end up giving us is a final velocity of the soccer ball should be positive. Should be positive. That's what we're looking for. Okay, so the last thing that we have to do is just plug in our values here. So we have 0.7 for the mass, 2, I wrote 0, 2 for the velocity, and then for the soccer ball, 0.45, and for its initial velocity, it's negative 0.2, equals 0.7, and then a final velocity for the basketball of negative 1.5, and then plus 0.45 for the mass of the soccer ball, and VSF, which we are trying to find. So if I do this, I should get 0.7 times 2 should give me 1.4. And if I multiply my 0.45 times 0.2, I should get negative 0.09. And then this was 0.7 times 1.5 should give me negative 1.05 plus 0.45 times VSF. Solve this for VSF. So move the 1.05 to the other side and then divide by 0.45. And if you do that, your final velocity should be positive 5.2 meters per second. Okay, positive 5.2 meters per second. So if I want to write this out as a vector, VSF is equal to 5.2 meters per second. We can say maybe to the right, just because of how I had specified that. So that is our final answer right there. Okay, we've got one example left to do. This is an inelastic collision. So we've got a scenario where the two objects are going to be stuck together after they collide. So generally we use cars for these examples because it's the most likely scenario that this would happen. 1,050 kilogram car is moving at 25 meters per second east and has a collision with a 3 times 10 to the 3 kilogram truck moving at 20 meters per second west. The vehicles lock together in the collision. What is the total velocity after the collision? So let's set up our positive and negative directions here. Positive to the left or to the west. And let's set negative to be to the east. I know that's a little bit different than what we normally do, but it's good to just make sure that we see that it doesn't matter which direction we set as positive, we should still get the same answer. So our total momentum before the collision is going to be equal to the total momentum after the collision. That is the key here for all of these problems. Let's just come up with some subscripts here. So right here, we'll say that the car, we'll call it C. The car we'll call C, and we will call the truck T. So what this ends up looking like is they stick together afterwards. So if I break this down, I'll get M of the car, the mass of the car, times the velocity of the car initially, plus the mass of the truck times the velocity of the truck initially is going to be all conserved and equal to, I'm going to call it B, which is going to mean both of them stuck together. So the mass of both of them times the velocity of both of them after the collision. So that is our setup. Now we know what the mass of the car is. Let's write all this stuff down. We know that the mass of the car is equal to 1,050 kilograms. The mass of the truck is equal to 3 times 10 to the 3 kilograms. And we can also find what the mass of both of them is going to be. We need to add them up. 1,050 plus 3 times 10 to the 3, which is just 3,000, gives us a total mass of both of them of 4,050 kilograms. Now we know both of their velocities beforehand. The velocity of the car is moving east, so that's going to be negative 25 meters per second. The velocity of the truck moving west initially is positive 20 meters per second. And our job here is to find what is the velocity of both of them at the end going to be. So all that's left to do is plug in our values. Mass of the car, 1,050, times the velocity of the car initially, negative 25, plus the mass of the truck, which is 3,000, or 3 times 10 to the 3, times the velocity of the truck initially, which is positive 20, is equal to the mass of both of them, which we said was 4,050, multiplied by the velocity of both of them at the end. And what I get is I multiply these two together. I add these two, and I add the multiplication of these two to this, and then I divide by 4,050 at the end. So if I do that, I should get 1,050 times negative 25 plus 3,000 times 20. And then if I do that, if I divide by 4,050, I should get, okay, so let's write this out. VBF equals, so I did this whole side here, 33,750, and then I divide by 4,050 on both sides. And what I get is that VBF is equal to positive 8.33 meters per second. So to write this out as a vector for our final answer, we should have our final answer in terms of 2 sig figs, so 8.3 meters per second, and it's positive, which means that it is going to the west. So our final answer should be 8.3 meters per second west. And there you have it, folks. That is it for our collisions in one dimension problems. So I hope that helped out. You could follow along with those. I have posted all of the solutions guides to the practice problems on the classroom, and I will be posting the notes key as well for any of you that want to maybe work ahead or work at your own pace. I do hope you're enjoying the videos and that they're helping out. Make sure that you remember we will be meeting tomorrow, so if you have any questions, bring them. If you don't want to ask them in person, you can always just shoot me an email or ask the questions on the comment section below, okay? Have a great rest of your day. We'll talk tomorrow.